Okay, problem number 3. Looks kind of scary because it has 10 parts, but basically it's just here to cover all the different kind of things that can happen when we have a limit. So let's take a look. So part A, limit as x goes to 0 from the minus of f of x. So that minus sign says come from the numbers that are less than, so we'll be here on the negative side. And we want to see what happens as we get really, really close to 0 in the x direction. So here I'm coming in from the x direction, I'm coming in, and I'm getting really close to this number 0, or this number 1. That's what f of x is going to. So for that reason, I'm going to say limit x goes to 0 from the left, or from the minus, of f of x, that is equal to 1. As we go to 0 from the plus, we go ahead and check as we go from the numbers bigger than 0, so that's going to be from the right side. So go towards 0, and it looks like we're getting close to minus 1. So limit x goes to 0 of f of x from the plus side is equal to minus 1. This makes part C free. If I calculate a left and right limit, then I automatically have information about the limit itself. Here, my left and right limit aren't equal, so this limit does not exist. So D and E. Right, the limit would exist if the left and right limit were equal, but since they're not, we get that it doesn't work. This limit does not exist. F of 0. So why is this something we're worried about? Because the limit doesn't care what happens at the point, just what happens near the point. So here, maybe we have interest in what f of 0 is on its own. And here I look where the dot is filled in, and that tells me what the value is. So f of 0 is equal to that filled in dot. So f of 0 is equal to 1. For part E, now we're looking as we get close to 1. Does that limit exist? Yeah, it looks fine. As I come at it from the left and right, it looks like it's going towards 0, so I'm going to write that down. Limit x goes to 0 of f of x is equal to, or not 0, limit as x goes to 1 of f of x is equal to 0. Because that's the number that I'm closing in on right here. And then what's f of 1? That also happens to be 0. So we can actually take a note to talk about something here, in that the limit as x goes to 1 of f of x is equal to 0, f of 1 is equal to 0. So by the definition, that means that the function is continuous at 1. So just kind of to refresh your memory on that, that's what we have. This statement here, E and F together, prove that f is continuous at that point. Okay, G. Now we're looking at 2. Limit as x goes to 2 of f of x. So f of 2 isn't defined, which actually answers H. D and E. But for part G, it's a little bit different, because the limit doesn't care what happens at 2, just what happens close. So if we look and see what's happening close by, we have that limit is equal to 2, because that's what we're getting close to. So this is what's referred to as a removable discontinuity. As x goes to 2 of f of x is equal to 2. Yes. Okay, and now finally we need to look at what happens for 6. So here if I look, I've got all this craziness coming, and it looks like this function keeps going up and down and up and down and up and down, and doesn't ever really settle on a value as I come at it from the left. So on that side, I'm going to say does not exist. But from the right, this is perfectly fine. I get really, really close to 3. So I'm going to write that down. And that's what I'm looking for on problems like this, is do you know what this notation means? The minus, the limit, the actual, what is the function equal to? And that's what I'm looking for there. So I said this function, this limit was equal to 3 when you came from the plus. All right, so hopefully that makes sense. These are really great problems. I like these a lot because they test your idea of, do you know what a limit looks like? And that's it for number 3.